InLoop Foam, and they're going to be talking about their pretty much, mostly the metallic foam and 3D printing, the benefits of that. All right. Well, we have Brett and Jacob with InLoop Foam, and they are going to talk to you about their new novel applications for foam. All right. Well,
absolutely. So yeah, to all the humans out there, everyone, my name is Brett Emery, and I am the co-founder and CEO of InLoop Foam Incorporated. And I am joined here today by my CTO and co-founder, Jacob Miskey. And today we'll be telling you about our technology that we have spent the last 6 years developing, and Jacob has spent the last 3 helping me bring to life. Our goal today is to tell you a bit about this technology and how we intend to use it to redefine foam for the engineer. All right. Well, here's how we make foams. Can everyone see the video?
Yep.
Hopefully. Great.
Yep.
Well, I'd love to go into super intense technical detail of exactly what's going on here. For the sake of time, I'll keep it brief. What we are seeing here is the physical tendency of thin threads to bend and coil, like we've all seen, likely if honey pouring from a spout. And when applied to a 3D printing system, such as the standard material extrusion machine seen in this video, we call it Viscous Thread Printing, or VTP, which is our core technology. This technology allows us to control the size and distribution of every coil you see here. And when deposited side by side and layered on top of themselves, each coil then becomes the cell of a foam. And this enables us to create foams without the traditional chemical approach, which has remained relatively unchanged in industry for about 100 years.
All right.
So, our solution and our technology trades chemistry for coils at its core. We did this by building AI-informed models that allow us to convert functionally any material extrusion system into a foam production platform. And what I mean by that is that we have built-in hardware and material flexibility, as the process is inherently compatible with any machine and material that can be pushed out of a nozzle. And we've already validated this on the common rigid and flexible polymers, all the way to metals such as copper, bronze, and stainless steel, and even ceramics and glasses. All of which we've done on machines ranging in cost from about $400 on the desktop to several $1,000s for systems that build on the order of yards. And we're able to finely control properties through the structure down to every cell and coil. All right. Well, so foam today, though, where does it stand? Foam is literally everywhere. Chances are everyone watching this is probably sitting on some or standing on some, and will probably go home and sleep on some tonight. But foam as a material, given its current production methods, lacks property controls expected of other common materials. All right. Well. Ideally, when working with any material, engineers, as many of us probably know from personal experience, want design freedom, rapid iteration, and a large property space. Because they want to have the right material for the right job, right when it's needed. These are traits that conventional foam fabrication methods have only really been able to provide in an inherently limited capacity because of the process being used. And we've been told as much by engineers at Oak Ridge National Lab, where both Jacob and myself have spent time developing this technology. All right. Well. So today, besides being inflexible, foam production is also inherently wasteful due to chemical constraints in actually creating structures that we think of as foams. In 2023 alone, North America produced an estimated 1.9 billion kilograms of physical waste byproducts in order to produce 2.8 billion kilograms of polyurethane foam, which accounts for also about 5.2 billion kilograms of equivalent CO2 emissions due to chemical off-gassing or even direct CO2 gas injection required to produce the traditional porous structure of foams. And this is only talking about polyurethane, which is a small subsection or just one subsection of overall foam production across the United States and beyond. All right. And this is what industry production looks like today. Whether it's large rolls of flexible polymers bound for upholstery or footwear, like we can see on the left here, or massive slabs of rigid foams for packaging and insulation, like in the middle, or bulks of aluminum and copper foams, which are highly sought after in aerospace, automotive, and chemical manufacturing, shown on the right. Conventional manufacturing focuses primarily on very large scale production of homogeneous blocks that require extensive additional processing in order to be shaped and assembled into end use components. And frankly, they're really good at it. Like they are, but they're still limited by their hyper specialized processes. They can make large bulks like this, but anything more specialized or more tailored has been largely out of reach. And so this is now. Oh, go ahead.
So then from here, what it goes into a subtractive manufacturing process, I guess, where they cut.
All right. Well.
Yeah.
All right. Well.
So depending on, of course, the end use application. If we look at, like, for example, one of those roles where I mentioned this is going into something like footwear. The first question basically comes down to how thick they need it to be. If it can be produced at the correct thickness, that's great. They don't need to shave it further usually. But what they will need to do is shape the actual footbed. And that means that there's inherently some shavings and cuttings that don't end up being put into end use products, and that end up not really being able to be recycled usually either, because of how foams are produced as thermosets. So mattresses are a great example as something that can be produced at nearly net shape in modern current components and current processes, but functionally at the end of life, there's nothing you can do with a mattress. They're one of the largest fillers of landfills in the United States, because the only option is basically to just put them there and wait. They can be churned up and used in some components that are like, if you've ever seen like recycled insulation, but those are very, very limited niche applications. So a lot of the time, subtractive is just a lot of carving until you get to what the shape that you need.
So since most of these are petroleum based,
Mhm.
Are they classified as hazardous?
The foams themselves,
or are there, or I guess not necessarily hazardous, but special processing. So like I can't just throw a can of paint in the trash.
Right.
It may not be hazardous, but there's another process that paint has to go through to dispose of it.
All right. Well,
so the actual solid waste is treated as fairly inert usually, even with more harmful foams like styrenes. Styrenes are infamously terrible for the environment, and there's not really easy ways to break them down in a safe way. But you can still mostly just throw away styrofoam as if it's anything else. And while that's still not great for the environment, the foam itself isn't treated as inherently hazardous in that state unless it's burned, at which point it releases mustard gas.
Yeah, it would be interesting to talk to somebody in the waste management, because I wonder if they actually pull this stuff out of incinerators because of what it produces.
Yes. So chances are, we haven't spoken with many people in waste management specifically on this topic, but based on what we've spoken, the folks that we have spoken to, I expect that would be a high priority for waste management, because things like mattresses and car seats, airline seats that are all common foams, one of their biggest requirements also is flame retardancy. They have to go through massive certifications to make sure that they're not flammable. And so even if it doesn't turn into literal mustard gas like styrofoam, chances are it would be a real nightmare, a real pain in the neck to get out of a furnace, since it's been designed not to burn.
All right, thank you.
So yeah, this is what current industry looks like. And essentially, it's been very good it's been matured into this large bulk realm of homogeneous chunks. And this is where we do not intend to start functionally. Our strength comes from the ability to directly produce custom foam products with gradient properties at near net shape, according to specific customer needs. So instead of creating these large blocks that need a lot of post-processing, we would be producing a near end use component with a much more customized properties. And so this is where we actually started. We initially developed the process with polymer foams in order to develop experience in models to be able to selectively tune properties. I think someone might be not muted.
Yeah, I'm going through and muting people right now.
Cool. Appreciate that. And yeah, so we developed these initial models and experience in polymers because they were easy to work with and also had their own selective uses. And we explored applying them directly for medical devices such as orthotic inserts, where we learned how to manipulate the actual shape and properties in order to fit specific customer needs. And during that process, we unlocked the capability to use the methods that we developed in polymers to be able to produce various metals. So in this case, copper, bronze, and steel are shown here. And we can leverage the same controls and programmability that we have with polymers to create similar structures in metals. And based on those capabilities, we believe that copper foam for specifically heat exchangers or thermal applications is our best first market because as an initial opportunity, it has very large margins and very high demand in the age of AI in which we live, and is conventionally technologically limited in ways that the lessons we learned in polymers, we believe, have equipped us to solve today. And so here are a few examples of what a few densities of our copper foams look like in a thin form factor. So ranging from high 0.7 relative density on the left, to a moderate 0.4 relative density in the middle, and a low 0.15 on the right. You can see how our foams are entirely composed of those entangled coils. It's basically one continuous thread bent upon itself for the entire body. And while the three here are all homogeneous, we maintain the ability to mix these together and with any density in between arbitrarily. So for example, Miski was just showing something that looks like a solid exterior with a porous interior. We're able to tune the actual density itself. That was intended to be a rudimentary heat pipe. So you can flow a thermal liquid through the center, and it would be able to mix with a high surface area with the actual heat pipe itself. Or if you wanted to, for example, I don't know, on the 0.7 high density, if you wanted to make a low density smiley face, that's about the same technical lift with the digital tools that we've developed for this process. So we have a huge degree of flexibility in actually where properties are being assigned.
I also wanted to mention on this component, we've been awarded research funding to look into fire screens and flame arresters using these copper foams.
Yep. Actually just came through the pipe, I think, beginning of last week. So exciting new developments are ongoing. So looking a bit closer at the microstructure level here, here's what legacy copper foams look like compared to InLoop copper foam. To give a little background on what legacy, like how it's being manufactured relative to us, they use what's known as a syntactic process, which is functionally where you take a big vat and you fill it with a bunch of sacrificial ceramic spheres. And then you pour the liquid metal over those spheres to fill in all the gaps in between, let that metal cool, and then you dissolve out those spheres, leaving behind this network of spherical voids and cells that are connected by these straight links. Well, if you look at our material, because it is that one continuous thread being bent and entangled over itself, we have a much more organic and curved structure. From the property perspective, this is significant in a few ways. For thermal and electrical conductivity, one thing they really care about is cross-sectional area. So if you look at the legacy copper foams, the actual cross-section between those links is determined based on the random placement of those spheres. So those sacrificial spheres. If you had happened to have an arrangement that had large gaps between spheres because of different jamming, then your links would then be very large. Or if those spheres were packed very closely together, then everything would then have a smaller cross-section for electricity and heat to be able to conduct over. So it's a much more probabilistic process. And so in contrast, since the deposition of our threads, the actual thread diameter is constant, the interface, that cross-sectional area is also constant between cells. The interface between the threads, so how the thread actually lays over itself, that is still fairly probabilistic. And so there's some variance there. but overall the connectivity of our coil-based foams are much more consistent than syntactic foams. And for mechanical behavior, there's also a really strong relationship here where those legacy foam links, as you can see, are all straight. They're all functionally at their maximum extension from the get-go. And so if you put them into...
even the careless order to they're not on
if you put them into tension, the only thing they can functionally do is stretch before fracture. Whereas if you put InLoop Foam into tension, the actual coil bent structure will first unbend, and in doing so absorb more energy before entering the state where those links are then straight, where legacy copper foam begins. And so we're able to absorb a lot more energy in that tensile regime. And then there's also some interesting relationships on how that relates in compression as well. But functionally, there is the actual differences are coming from the microstructure between the legacy processes and ours. And this is what generally that looks like.
All right, so I want to stop you here and see if anybody has any questions to this point. I'm not hearing anything.
Just thinking about other applications, I see the heat transfer and electrical, but I'm curious, you talked about the differences in foam structure, energy absorption, energy dissipation. Is this something that would go in like crumple zones for vehicles or other energy absorbing material for impact?
That is a great question. Feel like I now planted you in the audience to ask me that.
I tend to do that sort of thing.
That's why he's here.
Yes, that's exactly a major interest area for us, especially for more structural materials like stainless steels. Naturally, copper is usually not really interested in that area, but is still very interesting for thermal and electrical. But yes, for specifically being able to tune mechanical response is something that we have a big advantage over legacy processes over. And basically, I'll leave that for Miski to answer later because we have some specific slides to talk about that actually. But yes, we are very interested in applying this for impact absorption because of these unique properties, both in the homogeneous structure, but also the fact that we can tailor and tune and embed additional structures within the actual overall material. So if you have any questions after Miski goes through his slides, we'd be happy to answer them there as well.
What about insulation properties? Are there insulation properties that go with this? Because I know Brian's going to be interested in that, Mr. Crowley.
So potentially, but one of the things that is like right now we're showing our foam compared to a legacy open cell copper foam. It is theoretically possible to be able to both, especially in polymers, to make closed cell foams. And it is also theoretically possible to make closed cell like aluminum foam. Typically, it's not very common with some of the more exotic materials that we are able to work with. But based on our process, we are fundamentally limited to only open cell materials. And so while there are great examples of open cellular materials being used for insulation, it's not one area that we expect to have a major advantage in and haven't looked into it extensively so far.
One quick question. I think I may have missed a detail. Your cells are open between the coils of copper. Is that copper itself solid or is it a foamed material as well?
This is a powder metallurgy like process. And so the threads themselves do have some porosity to them. Right, if you go back to the slices real quick, right, on that left side there, that's 70% the density of solid copper, but it looks like a solid disc. And that difference between the pure solid 100% copper disc compared to that is that internal thread porosity, because this is a powder metallurgy based process.
Yes. And so one thing that also means is that we can actually, based on this being powder metallurgy, you can somewhat tune the microstructural porosity based on how you go through what's the sintering process, where you're actually fusing the powder into a continuous metal. But that's in a global effect. But because we can, on the kind of mesoscale, macro scale microstructure that we're working with here, we can control the local porosity from the coils. So we almost have two dials one localized and one globalized, for tuning a hierarchical porosity for these materials, specifically in the metals.
Yeah, I've read about one other process actually on the device, purposely induced porosity. It's a silencer technology. Just curious how your approach to maybe 3D printing a suppressor with this type of material.
We spoke with Alex Kingsbury at Enlight. It's a company out in the Pacific Northwest, and they do some metal printing work as well, laser heating of metal feedstocks, and they've been contracted by some people in the suppressor world. My brother has tinnitus, and he spent almost 10 years in the Army, and he's asked me about the potential for this technology for that as well.
This is Eugene again. The so what we're looking at here looks more like copper. We were looking at in the other photo looked gray.
That's a trick of the lighting.
Okay. So can you adjust the how much copper is in the foam? I mean, can you increase it, decrease it?
So
I'm just thinking, conductivity wise. I mean, if you had more copper in there, I mean, it'd be a little more expensive, but would it be better at heat transfer if you had less? I mean,
at this time, we receive a lot of our feedstocks from an external, partner. We've done a little bit of experimentation, and there is a lab that we are friends with who does like the filament production. We've spoken with them about how to tweak those filament parameters. There are some like limits on just how much metal powder you can fit in the feedstock and the sort of size of the particles, which then downstream impacts the micro, or like maybe I should call it the nanostructure, like the structure within the thread. Right. There is a lot of room for additional improvements on all the results that we have shown you and will show you in the rest of this presentation. But there's a lot of untouched potential there as well.
Okay.
Great. Then there's no more questions. I'll move on to telling you a little bit about our business model.
I have one more question, if that's okay.
Go for it.
Thank you. So we're seeing examples of copper being printed. By any chance, have you guys looked into doing metals such as Inconel, like nickel-based alloys?
Yes. Yes, we have actually. We right now in our lab we have a spool of Inconel that we're excited to try printing into this structure. The only reason we haven't done it so far is because that Inconel, as you probably know, requires very, very high temperature processing. And while we're using powder metallurgy and sintering rather than any kind of liquid handling, the temperature is considerably lower than if we were to try to directly forge or manufacture Inconel during conventional means. We currently do not have access to a kiln that is high temperature enough to be able to process the Inconel. There is nothing that we like in our process that would tell us that it is for some reason uniquely incompatible with creating these structures. It's just a requirement. It's just an equipment requirement essentially now for the stage of that we're currently in.
Okay. And is there like a rough timeline of when you think you'll be doing more of, let's say, Inconel printing? Because that's, I guess, mostly what interests me is that ability to be able to 3D print nickel in this form.
I think we should have a conversation, a follow-up about that, because if there is an interest for Inconel, we can accelerate that. We have friends with the high temperature kiln we need to get that done. Honestly, the reason we haven't done it is because we've been having a lot of customer demand on the copper, steels, bronze metals, but it's sitting there like ready to go once we have an actual customer to start with it.
Okay. Sounds good. Thank you so much.
Yeah, of course. Thanks for your question.
And I'd like to have a conversation too, thinking about that. Part of a fusion group, and one of the things that one of the options for the targets that actually generate the fusion or ignite the fusion is to make it a continuous foam string rather than individual beads that drop in, get hit, drop in, get hit. So that's a conversation I'd like to have after this.
Absolutely.
Let's have a follow-up. I'm interested in that. I've originally my degree was in nuclear science, and then I also got a dual degree with mechanical.
So I understand the sintering temperature. What temperature do you actually print the loops at?
Yes, great question. So functionally, the actual feedstock we're using, since we're just using standard desktop material extrusion machines, so like in the video I showed earlier, that wasn't a specialized piece of hardware. It was sitting on my desk next to me while I was working. So naturally, it's not working at liquid metal temperatures. The actual feedstocks we use are known as metal-polymer composite filaments, where it's basically just a polymer matrix with the metal powder suspended within it. So it can be printed as any other desktop material extrusion filament. So we're printing on the order of 210 Celsius in order to embed the actual structure. And then we go through additional debinding and sintering steps in order to remove the polymer and then fuse the metal.
I have a quick question about the parts geometrically. Is the shrinkage that you get during sintering, is that well enough understood with these kind of foam products to be able to print and then debind and sinter apart and have it near net shape?
So
yeah, you want to go ahead with this, Brett? I just wanted to show this card as an example. We're able to reproduce fine features.
Hold on, Jacob. I'm going to highlight you for everybody. I want to spotlight you. All right.
So we are able to produce fine features, even though the green body does shrink as it becomes the sintered body, right? So at first we were seeing a spread of between like 10 and 15% shrinkage, and we had to roughly estimate like the green body shape and then shave down to get to that. Part of what's great about working with foams is that people already understand that they're a bit flexible with their dimensions and usually in their manufacturing. When they're coupled in with a system, there is some give and take. There is some post-processing already kind of assumed, rather than printing solid metal bodies or kind of looking at that customer segment first. But I do want to say that we've really dialed in our ability to do this process, and we have our shrinkage pretty reliably between 13 and 14% now.
Yep. To add a little bit onto that as well, the actual shrinkage characteristics are typically not as strongly related to the density of the material so much as the bulk feedstock. So as long as your powder fill in your feedstock is consistent and your post-processing routine is consistent, it is fairly predictable. That's basically it.
Okay, yeah, that makes sense. I was trying to imagine if you get sort of the same bulk shrinkage that you would when the whole thing is near solid, versus is it kind of shrinking the filament but staying the same overall shape? And it sounds like it's somewhere in between. It's less shrinkage than I think I'm used to, but yeah, still some. It's interesting.
One thing I will add actually is that while it sounds like you have some experience also with sintering some solids with lattices, which we're also commonly compared to. We have found that because of our structure, that bent structure, like the actual buckled structure of the coils themselves, allow us to actually have greater resilience in surviving the shrinkage of debinding and sintering compared to structures that have straight links or solid sections where cracks can be very problematic. Essentially, if there's any kind of temperature gradient, normally that means there's a differential shrinkage, which can cause a fracture. But because our material is able to either compress a little bit and extend a lot more than if it was solid or had straight links, it's actually much more tolerant to non-uniform shrinkage than our conventional lattice structures would be.
Okay, yeah, that's really interesting. Thank you.
Mm-hmm. All right. Shall we talk business? So, our business model is fairly straightforward. We are intending to be a B2B manufacturing service network with per part pricing. So customers send us specifications and we'll ship them their parts. Our process is linearly scalable with more nozzles. So in order to actually get product out the door, we really can only need to start with one machine. And then if we wanted to double manufacturing, 2 machines, 4 machines, so on. Which means that we are very flexible and readily scalable compared to processes that need to be set up within a built for scale at the very beginning. And so with that path to scaling, we also can add more materials, which will unlock additional properties. Those additional properties then will unlock additional markets. And we do so with the relatively low capital cost of conventional off-the-shelf 3D printing equipment. Depending on the needs required, we can work with machines like Ender 4s or Ender 3s, my bad, where they can be a few $100s all the way up to very, very large scale. Foam R&D, I mean in the sense of essentially understanding how we can print and model our different materials so that they are predictable. We are looking to develop specifically models that allow us to understand how creating a specific microstructure can be consistent across different materials, but understanding what the actual downstream structure, its properties will be, are related to the input bulk properties. And so right now we use a data-driven approach to actually understanding that so that we're able to do inverse design to produce specific components as requested. But down the line, we'd like to be able to understand that if we can make this structure and we have these materials, here's the different properties we can understand or expect rather. So that's a big area of foam R&D for us. And then another large area of interest is this downstream potential for licensing and remote on-site manufacturing. So you can basically imagine that this process, if you were able to do it with just a single printer, you'd be able to create specialized high-performance components in locations that are logistically difficult or otherwise hazardous to conventional supply chains in ways that setting up a full metal foam fabrication would be impractical.
Right, Pat, did that answer your question?
I guess what I was driving at is we do SBIRs. Do you guys partner with SBIR companies, or is that something you just do on your own?
Misky, you want to answer that one?
Yes. So I worked for about 5 years with Physical Sciences Incorporated. They are a company that does a lot of SBIR and STTR work. InLoop Foam Incorporated, we are new. We have not won an SBIR or STTR yet, but we do look forward to proposing some work when the topic comes up. If you're a company that has experience with the program, we would like to speak with you about potentially working as a sub on your proposal with our material.
So, Jacob, this would be a good time to go ahead and mention your Cradle work.
Oh, yeah. In a moment, we'll present some numbers. Actually, Brett, do you mind?
Yeah.
I think it's the next slide. Or no, it's the one after that, the video. Yeah. So some key numbers here on the slide. When we showed the fracture toughness numbers to some folks at Los Alamos who do impact work for ballistics, they've come back to us and said, hey, we want to sign a CRADA with you. That is not in order yet. That is not in place. But we're planning on meeting with them in the next few weeks to establish that. They want to use our steel foams, our stainless steel foams for that impact absorption and ballistics work, because our fracture toughness compared to these reticulated homogeneous metal foams is just so much better. Yeah. We can
and Brad or Jacob, if one of you could put all your contact information in the chat. And Pat, I do have your email, but I don't associate names with emails. So all I have is a list of emails. And so I don't know that I would be able to decipher unless you put it in when you signed up. You know, that what email is yours. Thank you.
Awesome.
I will reach out to Pat.
Sounds good.
In the interest of time, actually, Misky, you want to just pick up from here?
Yes, I'll start here. If actually we just pop back real quick to the videos, the 2 videos, just to give people a reminder. For those who joined us a little bit late, right? Our process on the left, we're using a modified FDM process to create foams by coiling material stochastically. Compare this to what's happening in factories today when someone orders a custom piece of foam. Two guys on the other side of the planet grab a hacksaw and they start cutting at that block of foam, whether it's polymer, metal, or so be it. All right, so to the numbers real quick. When we looked at the existing metal foam market, we found that it's a low supply and growing demand. And that kind of market, existing players can charge a lot. Existing copper metal foam sells for up to $200 per kilogram. And we did a techno-economic model of our foam and found that we can serve that material for far less. Our feedstock is an inert metal-polymer composite filament, which is compared to existing solutions which rely on molten metal that's casted or loose metal powder, which is a fire hazard. We have a pretty wide porosity range, and we're trying to push those bounds to encompass everything that existing players can do. And that fracture toughness is a key metric that we've measured when we mechanically tested these copper metal foams. When we looked at the thermal tests for our copper metal foams, we were really surprised. We set up a couple heat exchanger experiments with different metal foams, stuff on the market today, as well as our copper metal foam. And we found that we could produce a heat exchanger with a better cost per watt of cooling because it was able to remove so much heat from PC, a hot plate, basically. And we can also provide variable 3D porosity, which is critical for certain applications in thermal and mechanical work. Some of the numbers from an experiment are presented in these very simple charts here, just to give you a sense of how we compare to the competitors. We can provide greater cooling power with a heat exchanger for the cost of aluminum. Aluminum fins are used generally across industries. You've probably seen an aluminum fin heat exchanger on your PC, your tower at home. They're used in automobiles. They're everywhere. And the metal foam market for heat exchangers is growing. And we want to be that service manufacturer to produce the top of the line custom heat exchangers that can outcompete aluminum or copper metal foam from existing suppliers. On the next slide, we want to mention also, because it's in the drinking supply, AI, right? Some of these massive chips now that are being touted on stage, they don't actually release heat evenly. Some sections of the chip may release a lot more heat than others. And so when you put a homogeneous finned heat exchanger on top of them, it's not as efficient as it could be because you're trying to apply a uniform solution onto a non-uniform problem. But we can produce a heat exchanger which is thicker or not as thick, more sparse in sections in order to move that heat most effectively from the uneven source to an even cooling sink. From Jeremy, we have you looked at radiative cooling, not just conductive? Radiative cooling generally involves higher temperatures for it to compete, with conductive or convective solutions. For our bare copper solutions, generally when we start to heat them to the point where radiative cooling becomes substantial, they start to oxidize in air. So we do need to do some passivity work, basically cover the metal with a very thin layer such that when we really get them hot, like glowing hot, they don't oxidize, and which of course impacts the experimental results. So radiative cooling is something that we've just touched the surface of in terms of R&D, but I'm very interested to look more into those numbers later. Next slide, we transition a little bit away from the metal foam, which is our focus right now, towards some other things that we've done. Oh, space-based systems. Yeah, in space you don't have to worry about oxygen, so radiative cooling would be very interesting for metal foam heat exchangers. In lieu of time, I do want to touch on the last few slides, but please shoot us an email if you want to talk more about metal VTP, metal InLoop foams in space. In case anyone here cares about programmable mechanical responsive foams, Brett and I presented this work at a conference 2 years ago where we've embedded low density zones in fingers and hands to create these soft robot hands for robotic devices that need to handle fragile objects and characterize how they reacted as you pulled strings that were embedded in the foam. On the next slide, we talk a little bit about metamaterial foams we've done. So we realized that if you pattern high and low density foam in array patterns, you get this difference in compliance and rigid directions. This may be useful for impact absorption, maybe a value to making sure that when something is being loaded, it doesn't deform to a certain degree, or maybe the deformation occurs in a certain direction. So we can redirect how forces move through structures. And this, I won't go too far into it, but this has been picked up by a bunch of other researchers who are looking into mechanical cloaking, which is the idea that you can push on something and then the object inside is not perturbed and that force moves around the object. So there's some interesting research happening right now on mechanical cloaking that this is related to. On the next slide, I just provide some color maps to that work as you compress this metamaterial foam that we've entirely printed in one piece, all in one machine, no post-processing. We're able to get the foam to shift in one direction rather than another, just by arraying those unit cells appropriately. Next slide. Recently, we've been doing some printed metal work for undersea vehicles, specifically autonomous undersea vehicles. And just yesterday, one of InLoop Foam's advisories was in DC presenting this work to DARPA. Less so the viscous thread foam, which is our proprietary IP, and more so just general competence in metal FFF is what this work is feeding into. On the next slide, I just want to mention some next steps so people here have a context on what we're looking at next. Beyond all of your interests and your requests and these follow-up calls we're going to have, I just want to let you know that we're continuously integrating other technologies, such as conventional printing with this viscous coiling printing to give design flexibility. We're adding new materials, obviously interest in Inconel. We also are looking at aluminum, glasses, ceramics, as well as alumina. We're working on our manufacturing pipeline, figuring out how to present someone with a form or be able to specify what they want accurately so there's less back and forth. And then building out these models we have for manufacturing to improve our reliability, like the shrinkage question that someone brought up earlier. And also, we're trying to increase our volume. Right now, we can produce foam samples basically the size of my hands put together, but we're working on producing foams at the meter scale in our own shop. And then last, I want to talk about our plan and milestones. At the moment, InLoop Foam is incorporated. We're a brand new company. Brett and I are rapidly learning business development together. It's what we're doing right now, and we're fostering this R&D and building IP every day. As we look forward, we know we have to scale up. We're going to have more customers. We're going to have more pilots, and learning how to retain the same skill at the desktop scale as we get bigger is going to be something that I see as a coming challenge. And then I think this is our last. We just want to ask, of course, if you have any opportunities that you know of that you can send our way, please let us know. We're looking for non-dilutive funding, grants, or contracts. And of course, all of your ideas for cross-science and cross-industry applications is incredibly valuable. Thank you so much for your time.
All right. Thank you, guys. Hey, if you go back a couple of slides to where you had that list.
This list?
That list there. So you're talking about adding additional materials.
Mm-hmm.
So some, you said glasses. Now, what about fibrous? So like basalt or, not asbestos, but those kind of things to improve your structural.
We actually, we've done some work with this with chop fiber. Specifically, actually, during our time at Oak Ridge National Lab, we worked on a printer that was, I think it was 8 feet by 16 feet build area, with a 1/4 inch nozzle diameter, where I used chopped carbon fiber filled ABS in order to create foam that had coils on the scale of a few inches across, and then the entire structure was about 3 feet in diameter. And we proved that, yes, it is the physics of deposition and that bending coiling motion still apply when there's chopped fiber inside the actual filament itself. Continuous tow cables, which is what I think you're thinking of primarily as having one continuous fiber throughout the entire thread, is something that's also of great interest to us, but does have more of potentially additional effects on how easily the material is able to bend and fill that coil pattern. So essentially, it may require a few extra physical models, but as long as the thread can deform, we can make coils out of it. And if we can make coils out of it, we can make a foam out of it.
Interestingly, I've read the chopped fiber, the fibers tend to align, so you don't get all of the strength benefits of carbon fiber. I wonder if your coiling mechanism would actually, in a high density foam, actually gain a lot of the multi-directional benefits that you usually get from carbon fiber that you lose in just standard 3D printing because the chopped fiber tends to align.
That's very interesting, actually. We didn't end up having time to conduct a lot of mechanical tests on the specimens. It was more of proof of concept. But I think, yeah, you're probably right about that.
We do have chopped fiber filament, carbon fiber filament. We could run those tests. It makes sense. I think your hypothesis is very sound. Do you know what industries in particular care about 3D printed homogeneous fiber composite structures like that?
I do not.
Yeah, I mean, I would say, I mean, the space industry is going to be interested in that. Anywhere where you're looking at shielding from radiation, you know, some where they can you know, they're going to want to control the structure, or you know, I mean, there could be. That was going to be my next question was, you know, can you control electrical properties like resistivity and conductivity, and you know, that there could be applications on smaller scales for stealth and invisibility to radar.
Yeah, with the carbon fiber filled polymer foams, I realized that they actually work really well as broadband absorbers because the inherent randomness in the foam helps ensure that there aren't any resonances.
Okay. Yeah, and that's key for stealth.
Yes.
It's not just the reflections, but the oscillations at connection points or at angles that cause a frequency to be
preferential versus
emitted. Yeah. Trying to walk around that one, but
the sensitive topic.
All right. So anyone else have any questions, thoughts? You want to go back to your last slide?
Yeah.
That's got your contact information on it. Yeah. So I want to thank you guys. And again, yeah, this is the big thing that we try to do is one, to big things is make people aware that this technology exists and what it can do. But what we do need is the community's help in networking this solution to find the people that have the pain that this solution would solve. And it doesn't have to be in your industry. There are definite cross-industry, cross-science applications for this. Just in, you know, I can see some in the fusion work that I've been doing. I can see it in electrical properties and insulating. So we're looking for, you know, complementary too. We had someone earlier talked about SBIRs and wanted to include them in an SBIR. I mean, this is great. This is why we're here. So I appreciate that. I want to thank everyone. And then I will give one last chance for questions. Brian, go ahead.
I found this presentation to be extremely interesting. Literally every sentence. I'm doing a lot of the same work, and I'll reach you guys offline, and we'll start collaborating.
Thank you very much.
Yeah, thank you. That means a lot. It's been a wonderful opportunity to be able to present to such a wide audience with various fields of expertise. So this is exactly why we do it. I'm glad you enjoyed it, Brian. Thank you.
And so now, you were introduced to me by Chemo. Are you doing any work with chemo on a tacit side of it? Tactile side of it? There we go. That's the word.
There could be collaboration, certainly, but we'd be open to thinking through that. Happy to advise as well, because I've been, in this technology commercialization game for quite a while now. So here.
Yeah, we've spoken with Chemo as from the business perspective, and he has given us some great advice, as well as the fact that we originally got connected by one of our colleagues, now works for him. And we've also put our materials under more than a few gel sites as well. So there's certainly quite a bit of overlap, even in the kind of parallel tracks.